It's with great pleasure that I can introduce you today to Professor John Ousterhout, flown in all the way from Stanford, California, to give to us a talk about can great programmers be taught? John Ousterhout is the Bosack Lerner Professor of Computer Science at Stanford University. In the past, he has founded 2 startups. Sorry. And he's a member of the National Academy of Engineering and has received numerous awards, including the ACM Software System Award and the UC Berkeley Distinguished Teaching Award. He's also the inventor of the Tickle programming language. And today he's here because in 2019 he wrote a great book called A Philosophy of Software Design, which many of you in the audience may have read. Maybe you've even prepared some questions. You can hold them until the end of the talk. And today, without further ado, we're really looking forward to going a bit deeper into these ideas. So, welcome Professor Dr. John Ousterhout. Here's to a great talk.
Thank you very much for inviting me to talk here. Software design is just one of my most favorite things to talk about. So I hope I can infect you with a little bit of my enthusiasm today. So for background, people have been programming computers for about 80 years now, and yet we still have no agreement on software design or even necessarily what good programs look like. And in fact, to my view, there isn't really even a whole lot of discussion on this topic. That's bugged me for a long time. And this talk is going to be about some things I've done over the last decade to try and increase the general sense of awareness of software design in the software community. But first, a couple of things. As I said, there have been things that have been bothering me for a long time. 2 things in particular I want to mention. The first one is this question. What is the most important concept in all of computer science? And I'm going to ask you for some input on this in about 10 seconds, so think about it. If you had to pick one idea that is used in every field of computer science, software, hardware, theory, artificial intelligence, is there one fundamental, most important overall idea that dominates our field of computer science? Anybody want to offer some ideas? Raise your hand, we'll give you a mic.
Divide and conquer.
Divide and conquer. That's a good one.
Abstraction.
Abstraction's a great one.
Communication.
Communication, great one.
Information.
Information. A few more.
Complexity.
Complexity.
Interfaces.
These are all great ideas. So one more.
Scalability.
Sorry?
Scalability.
Scalability. These are all great ideas. So I asked Don Knuth, who's at Stanford, and some people think of as sort of the godfather of computer science. I asked him what he thought, and he got it almost right, although people would probably say if he said it, it is right. He said layers of abstraction. So what I would say is problem decomposition. How do you take a large, complicated problem and chop it up into pieces that you can solve relatively independently? I think this is the fundamental essence of our field that threads through all of the various disciplines of computer science. And yet, nobody teaches it. There is, as far as I know, aside from the course I'm going to tell you about, there's no course anywhere in the world where the notion of problem decomposition is one of the fundamental concepts taught in that class. And I've wondered, how can that be? This is the most important thing in computer science, and nobody attempts to teach it. What's going on here? Second thing that's bothered me for a long time, well, first, we know that there are huge differences in productivity between different programmers. Elite programmers are easily a factor of 10 more productive than average programmers. In fact, I was told by a Google vice president, he did a little test one time where he took his lieutenants and he asked them, if you had a choice, either I take your top programmer or I take your N bottom programmers, how large would N have to be before you'd give up your top programmer? A typical answer was 300. And yet, as far as I know, nobody attempts to teach the skills that make people elite programmers. Again, how can that be? It doesn't make any sense. So I've been wondering for a long time, is it possible to teach great programmers. Actually, I did a survey of my colleagues. About half of them thought it was possible. Half of them thought it was just some sort of God-given gift that either you have it or you don't. Well, it turns out at one point I read a book, one of my favorite books, called Talent is Overrated by Jeff Colvin. It's a great read, a nice airplane or beach read, not very long or difficult to read, where he goes through study after study after study and shows that the difference between the really top performers, sort of the world-class performers in a particular area, and just the average people is not any sort of fundamental talent that they're given. It's basically how much they have practiced. It's how much deliberate practice they've had. That's the only thing that really distinguishes them. So I read that book and I thought, and I believed the studies again. I thought, okay, it's got to be true for software design also. It has to be possible to teach this. But then the next question was, okay, who's going to do it? Well, the problem is, not most faculty, unfortunately. Here's what happens. If you're going to be a professor, you start off as a graduate student. You write a bunch of code as a graduate student, and typically you make fun of what a terrible coder your professor is. And then you become a professor, and you decide coding is for graduate students, so you stop coding, and then after a few years, your students make fun of what a terrible coder you are. And since the only way, really, historically, to become a good software designer is through personal experience, no faculty have the experience that could possibly do that. So there's pretty much nobody in American universities, at least, that can do that, except, it turns out, I'm not a typical professor, so I love to code. I mean, code is one of the 2 or 3 things I live my life for. If I don't write 5,000 or 10,000 lines of code a year, I feel disappointed in myself. So over the course of my career, I've written something like 300,000 lines of code, including I've led teams that have built 3 operating systems from scratch and 5 file storage systems, a scripting language, a toolkit, 2 debuggers, 5 graphical editors, 2 parallel build systems, on and on and on. So I love to code, and also I love this notion of software design. What makes code better or worse? So I've been thinking about it over the course of my career, and I figured, well, if anybody's going to do it, I've probably got about as good a shot as anybody. And by the way, I should say, even people who are great programmers often don't really know how they do it. Early on in this whole process, I managed to wangle a lunch with 3 of the people that I think are among the best programmers in the world, all at Google at the time. Ken Thompson, one of the original authors of Unix, Jeff Dean, one of the authors of many of Google's major pieces of system software, and Rob Pike, who has a long and illustrious career. And I sat down and asked them, so what are your secrets? What do you see as the keys? What is it that makes you a great programmer? And surprisingly, they were all of them pretty inarticulate. It was very difficult for them to put into words what they did. I still believe they're great programmers. It did not change my view of them, but it just goes to show you that even people who do it and do it very well aren't necessarily conscious about how they do it. So anyhow, I figured if anybody's going to do it, maybe it should be me. And then the next question is, well, how do I do this? And I debated what to do, and finally I decided I'm just going to give it a try. I'm going to try teaching a class and see, can we do that? So I developed a new class at Stanford called CS190, Software Design Studio. And the idea of this class is that it's not taught like a typical computer science class or typical programming class. It's taught more like how English was taught, at least when I was in high school a few centuries ago. And the way you learn English is that you write something, and then your teacher takes it and marks it up, and they give it back to you. And then you rewrite it, and they mark it up again, and give it back to you. And you go through this process of getting feedback and rewriting and iterating over that, and that's how you learn to do it. So I decided that's how the class would work. It's a relatively small class. We do 3 iterations, which is as much as we can do in a 1/4 course. So in the first 3 weeks of the class, the students get the largest possible project that I think they can execute in 3 weeks. So it's not huge. And software design issues become more interesting the bigger the system gets. But typically a few thousand lines of code. They build from scratch. I give them no clues about how to do anything. And then we do code reviews. The students read each other's code. I read every line of code by all of the teams. And then we do code reviews in class. And as well, I meet with all of the groups and go over my code review. And then they rewrite and redo things. In the second phase, they revise and add a few more features. We do another round of code reviews. And then in the third phase, they start another whole project from scratch, another design from scratch, and we do code reviews for that. So we do 3 cycles over the course of the quarter. It would be better if we had a semester and we could do a 4th cycle, but at Stanford, we don't have that. So one of the attributes of this is that I personally read every line of code that each of these, there's 9 teams of 2, write over the course of a quarter. And that means there's 3 one-week periods where I basically have to read about 20,000 to 30,000 lines of code. So my colleagues look at me like I'm some sort of a crazy person, and maybe they're right. But actually, for reasons I'll get into in a bit, I actually kind of enjoy that process, and it's been a really interesting educational process for me. So that's how the class works. Now you're probably wondering, okay, but what are the magical secrets? How do I become a great software designer? Well, first, I don't claim to have all the answers. Nobody taught me software design. The only way I figured this stuff out is by writing code and reading code and looking at my own code and other people's code. And so I have some things I think I've learned, but I don't claim to know everything right now. But the class is based on about 8 or 10 almost philosophical bits of concept, like classes should be deeper, or define errors out of existence. And I present these sort of principles to students. Typically, I don't expect people can understand them in the abstract. They're just too vague. But what happens is they write their code, and then we do code reviews, and I review the code. And then I can point out, okay, notice this piece of code ended up really complicated. It's because you violated this one principle over here. If you revised it in the following way, according to that principle, then the code will become cleaner. And so they go off and do that and come back, and they can see, in fact, the second projects are always amazingly better than the first project. The students come in, they're almost kind of laughing when we do the second round of code reviews because they realize how bad their first project was and how much it's improved. So we use these concepts. And then the other thing is I try and identify a set of red flags. So red flags are very precise, objective things you can observe in your code. So easy to do, even if you don't have a lot of experience, you can see if this red flag exists. And those are really helpful because they give people clues that it's time to rethink. And so I tell the students, even if you get everything wrong initially, if you just look for the red flags and keep fixing red flags until there aren't any more left, you'll probably be in an okay place, not a bad place. So red flags are super useful, particularly for people early in their career where they don't have a lot of experience yet. So what I now like to do is I'm going to take you through some of those concepts. I don't have time to go over all of them. The 4 that are in red on this slide, I'm going to go over in a little bit more detail. So the first one is classes should be deep. Here's the idea behind this. And by the way, I would say that all of these ideas, everything is about managing complexity. Complexity is sort of the enemy, the fundamental enemy of software development. So everything you're going to hear is about either trying to eliminate complexity or trying to somehow manage it and hide it so we don't have to be aware of it most of the time. So this idea, classes should be deep. If you think about a class as a rectangle, like I've drawn on the slide here, and imagine that the area of the rectangle is the useful functionality that this class provides to the rest of the world. So think of that's the benefit that this class provides. And then imagine the top edge. That's the interface for the class. An interface is everything someone needs to know in order to use the class. So it's not just the function signatures, but lots of other things. If there's dependencies and ordering and things and side effects, all that stuff is part of the interface. So interface is cost. That is, people have to learn that in order to use the class. So the best classes are those with the most benefit and the least cost. So that means the smallest possible interfaces and largest amount of functionality. So I have names for those. So a shallow class is one that doesn't have a whole lot of functionality and it has an enormous interface. So you spend a lot of time learning this interface, and you have to remember that, and you don't get back a whole lot for it. A good class is a deep class, which means it has a small interface and a lot of functionality. So you don't have to learn very much, but you can get a whole lot done once you've learned that little piece. Now, this is basically a reformulation of an idea from a really classic paper from around 1970 by David Parnas, one of my 2 favorite papers in all of computer systems. So if you're curious, you can go back and read the paper. But he basically came up with this idea. I've simply given it a slightly different name. So let me do some examples. Here's an example of a, sadly, very typical shallow method that I see. And this is an actual method that I saw. I can't remember if it was a student project or when I was doing a startup. But if you look at this method, the interface for the method, that is what you need to know to use it, includes the entire implementation. So there's no abstraction. Nothing's hidden. It hasn't bought you anything at all, basically. And in fact, if you think about it, in order to use this method, I have to actually type more keystrokes than if I just typed in the body of the method instead. So it's a strictly lose situation. There is no benefit, there is only downside to this method. What's going on here? Well, what's going on is that the generally accepted wisdom for people writing programs is that classes and methods should be small. And sort of maybe the extreme example of this is the book Clean Code, written by Robert Martin, where he says things like, the most important thing is that a method should be small. The next important thing after that is it should be even smaller. A method should have at most one control structure in it, like an if or a while. And the body of that should be at most one line that invokes another method. This is pretty extreme. The result of applying this sort of consistently in an environment is what I call classitis, where the goal is to have as many small classes as possible. Rather than add something to an existing class, no. You want something new, make a new class for it. And by the way, that class should be as small as possible so you can add many, many more classes to fill out the remaining features. For example, in Java, for many years, if you wanted to open a file and then read serialized objects from that file, you had to create 3 objects. First, a file input stream, which for some reason didn't do buffering. It would invoke the kernel for every character you read from the file. So if you want buffering, you have to create a separate class, buffered input stream based on that. So then the question is, well, who doesn't want buffering? And probably the answer from the Java people would be, well, not everybody, and so we felt like it should be separate, because not everybody wants it. What I would say is, no, you want to design for the common case. So not everybody wants buffering. It's true. It's only 99.9999, maybe 3 or 4 more nines % want it. So make that the common case, and then have an extra method people can call if they want to replace the buffering with their own buffering mechanism. But don't make people create an entirely separate class for that. And in this world, then, if you wanted to read serialized objects, no, sorry, that's not included. That's an unbundled, that's a la carte. It doesn't come with your meal. You have to create a separate class to do that. So to me, this is bad design, because what happens is you end up just dying in a sea of interfaces. And so the amount of information you have to keep in your mind about all these interfaces to get everything done is crushing. So I would argue length isn't the most important thing. Now, generally, all other things the same, making things smaller usually makes them cleaner and simpler, up to a point. But the most important thing is to make things deep. Make the classes deep, because that's where you get leverage against complexity. I'm hiding a lot of complexity behind a really simple interface. That's how we get leverage. So I want to do a quick survey about how many of you at some point in your career have been told, if you see a method longer than n lines for some value of n, you should break it up. How many of you have been told that? Yeah, pretty much everybody. Okay, now let's just see how small n has gotten. So first, how many of you have heard of a value of n, say, that is 50 or less? You've seen it, 50 or less. What about 20 lines or less? Any methods longer than 20 lines you should break up? We're getting down, not so many. What about 10 lines? Anybody been told longer than 10 lines? Yep. Okay, let me go really extreme here. Anybody been told 5 lines or longer and you should break up a method? Maybe one hand. Yeah. So I think we've all been taught this. Actually, it turns out in our Stanford introductory classes, we also teach people to break up long methods. And I've had conversations with the instructors of the class about what should we do about that. And the answer is, I think, at that level, when people are just learning how to program, we just need to force them to break things up so they start thinking about that, but they don't really have enough understanding to be able to do the kinds of things I'm going to talk about here. So maybe that makes sense early on, but it's something I think you have to unlearn very quickly. That, yeah, shorter is generally better, but it's not the most important thing. So here's an example of a deep interface, maybe one of my favorite interfaces in the world. This is the file I/O mechanism in the original Unix system, now, of course, in Linux. Five functions, all really simple. There's nothing complicated in any of these APIs, except the only one thing is the flags option for the open calls. A little bit, there's flag bits that interact in a bunch of different ways. So there's a little bit of complexity there, but other than that, these are really, really simple functions. What's the functionality you get for that? It's typically hundreds of thousands of lines of code in the kernel, implementing everything from how you store files on disk and manage disk blocks to path lookup and directory management and permissions and scheduling disk and a block cache and device independence. There's an enormous, enormous amount of functionality behind this lovely, simple interface. So to me, this is one of the most beautiful interfaces around. Now, you probably look at it and say, Well, duh. I mean, this is the way you do it. Of course, how could anybody have been so stupid to do it a different way? Well, if you look back at the world before Unix, before Thomson and Ritchie came up with this interface, they didn't do it this way. The interfaces were incredibly complicated. And one of the beauties of Unix is its ability to have come up with these really, really beautiful, deep interfaces. All right, that's my first concept. So classes should be deep. And by the way, that applies not just at classes, but it also applies at individual methods within a class. They should be deep. Simple interfaces, nice functionality. And at higher levels, subsystems or services, again, same thing. Simple interfaces, lots of functionality. So it applies at every level in the system. Okay, so next topic is general purpose classes are deeper. So here's the issue. I'm sure all of you have faced this. Certainly I know I have many times. When you're starting to build a new class, there's two ways you can go about that. One way is you can try and build something very general purpose from the start. That's the right side of the slide here. The left side says, well, no, don't overdo it. Just build what you need today and maybe a little bit specialized for the functionality you need today. And then plan on refactoring it, and you can introduce generality later on if you decide you need it. So let's just do a little survey. I want to see how many of you kind of side with one of these approaches or the other. So show of hands, how many would argue for general purpose design from the start? Okay, and now how about start specialized and generalize later when you know what you need to do? It's like 3-to-1 or 4-to-1 in favor of starting specialized. And by the way, that was my initial thinking. In fact, the first time I taught the class, that's what I thought. I didn't really have honestly, I had no way of really choosing between these two, but somehow it didn't seem like you should build stuff you don't need. And so that's what I told students in the class. It turns out that is absolutely wrong. I've subsequently changed my mind. The problem with this approach is you end up with really complicated interfaces and entanglement where various classes all depend on each other in funny ways where it's very difficult to make changes. Whereas if you go the general purpose route, things end up simpler and deeper. It's very, very counterintuitive. But let me give you an example to illustrate that. So this is from the second time I taught the class, where the first project was people had to build a very simple text editor that would display a file on their screen, and simple, you could insert text and cut and paste and so on, and delete characters. And as part of that, they had to build one class that was going to store the text of the file. And they had to design the API for that. And pretty much everybody would do specialized APIs. They think, I'm going to build the features in the text class that I need. So I need the ability to insert characters when somebody's typing, so I'll have an insert character method. I'm going to need to handle the backspace character, delete the previous character, so I'll have a backspace method. And I'll have another method, delete, if I'm going to delete in the other direction. And a third method for deleting if I want to delete the whole selection, and so on. And so the result of this is end up with a huge number of methods. Pretty much one method for every operation in the user interface. And the result of this then meant that there's this tremendous information leakage with the user interface. Things like, you notice these APIs include things like cursor object. Cursor has nothing to do with text. That's related to the graphical user interface. Or selection, again, doesn't have anything to do with the text per se. And so the result is that there was entanglement between the implementation of the text class and the rest of the user interface. And furthermore, every time you add a new operation to the user interface, you now have to change the API of the text class to support that. The alternative is to take a general purpose approach. So you only need two methods for this. An insert method that inserts any amount of text at a particular location in the file, and a delete method which deletes the text between two locations in the file. And then all of the user interface operations can be expressed as very simple invocations of one or maybe a couple of calls to these methods. And so the result is you end up with fewer methods in the class and a much better modular decomposition. Now we have clear separation between the text, how it's managed, and the user interface. They can each be designed independently from each other. And by the way, as part of doing that, we had to define a new thing called a position that represents a location of the text file. So now in the user interface, the cursor is just one position object. The selection is two positions that delineate the ends of the selection. It made everything way cleaner and way simpler. So I've changed my mind on this. If you'd asked me 15 years ago, I would have given you a different answer. I would have sided with all of you who voted for the special purpose thing. But today, I'm 100% convinced about this, because as I've seen the class evolve, over and over and over, the same thing comes up where the students build these APIs that are special purpose, and they're complicated and entangled. So what I would argue is you should design your classes to be what I would say is somewhat general purpose. So in terms of the functionality, what it does, focus on today's needs. Don't build a lot of functionality you don't need. So if you're building a text widget, don't feel like you have to build a globally geo-replicated database with atomic transactions to support that. You don't need that functionality. But when it's time to do the API, that's where you make it general purpose. So design the interface so it is not specialized for what you're doing right now. Try to make it as generic as you possibly can. And it turns out if you do this, you may never use this class for a second purpose. Maybe it really only will be used for that first thing. But even so, I promise you it will be simpler and easier to maintain. It's just been shocking to me how effectively that idea works. And so I now think if I could give people one piece of advice about software design, it's try and eliminate specialization in any form, either in the interfaces or in the implementation. You want to build things general purpose. One thing that solves many problems. Really, really, really important. But again, it's kind of counterculture. If you ask people out there, they'll probably say, no, don't do that. But try. I'd say suspend your disbelief and try it, and you'll be amazed how well it works. Okay, next thing I want to talk about is the mindset. So another really, really crucial thing about if you wanted to be a good software designer is you have to have the right mindset. And there's two ways, I think, of thinking about software design, tactical and strategic. So the first approach is tactical. So when I say someone's programming tactically, what that means is you're focused on achieving some short-term goal, like you want to fix a bug or get the next feature working. It's kind of hard to argue that that's a bad goal to have. Surely our job is to actually build systems that work. But in the tactical approach, that goal kind of overrides everything else. And so you say to yourself, well, I'm a generally good designer. I care about software design. But if I'm trying to get this thing working, and particularly if I'm under a deadline, and I have to make just one little teeny tiny kludge, that's okay, right? Because overall, I'm a good designer. I try and design stuff. Well, I would say, sadly, that's not okay. Because the problem is that you're not just doing this once, you're doing it over and over again. And you're not the only person. The other 1,000 developers in your project all have the same mindset. And some of them may think that it's okay to have 2 or 3 little kludges or 5 kludges instead of 1 kludge. And so this is where technical debt comes from. You end up with a design that's not very good, and you end up with a code base that is complete spaghetti code. So I think one of the most important things to realize about complexity is incremental. It isn't that you make one fatal, horrible mistake and that completely blows out your complexity. That almost never happens. It's a whole bunch of little things that just gradually build up over time, and then they become this huge problem. And the problem with this is because it's incremental, once it's there, that also means there's no one fix you can make that's going to solve it. It's hundreds or thousands of fixes. So it's the pain of fixing it just becomes unbearable. And typically, most organizations don't have the organizational courage to even attack that. And so it's just there forever. You can't ever get rid of it. There's a particular personality type I call the tactical tornado. This is a person who takes this tactical programming to the extreme. They work at tremendous speed, typically solving 80 to 90% of a problem, and then they declare success, leaving a wake of destruction behind them for all of their colleagues to clean up. And sadly, in many organizations, the management thinks of tactical tornadoes as heroes. Oh, this is my go-to person when things are really bad. Just out of curiosity, how many people think you have seen a tactical tornado in your vicinity programming? Yeah, we all know who they are too, right? So management may think these people are heroes, but the rest of their cohorts don't think they're heroes because we spend all of our time cleaning up after them. And then management says, how come you're not getting as much work done as this other person? At which point you kind of want to explode and tell them, well, because you're cleaning up this other person's messes all the time. So anyhow, the bottom line here is that yes, code has to work, of course. But working code is not enough. That can't be the most important goal. Instead, I would argue for the strategic approach. So in strategic programming, the most important goal is to create a great design. That's the most important thing. Of course, the system has to work as well, yes, but the most important thing is to create a great design. And the reason for that is because not only do we want to get things done quickly today, but we want to be able to get things done quickly tomorrow and next year and the year after that. And if you think about at any given point, if you enter a software project, probably most of the development on that software project is still to come in the future. You're probably not more than halfway done. And so making life better in the future is a really, really important goal. So this means you have to try and minimize complexity. And sadly, it means you have to sweat those little details. You just can't let yourself introduce little kludges because those will pile up. So on this slide, I've got this is a total imaginary graph. I wish we had a real graph like this. It actually could show, the effect of various approaches. But imagine we have time on the x-axis and the total cumulative progress of a project on the y-axis. And you compare strategic to tactical. So what happens with tactical programming, that's the red dashed line, is you start off and you're developing really, really quickly, faster than on the strategic line. But complexity increases and development goes slower and slower and slower and slower. And eventually it can practically come to a halt. Whereas with the strategic line, we accept slightly slower development speed. Basically, we're investing a little bit. And then the complexity doesn't build up as fast. Now, sadly, it will still build up, unfortunately. There is no way to win against complexity. In the end, we can only slow it down. But eventually, what will happen is you'll be developing so much faster in the strategic curve that you'll actually be ahead of where you would have been on the tactical curve. So I really believe that fundamentally there is a crossover point. Now, the real big question is, where is that crossover point? Is it during my lifetime, for example? Will it happen before our next release? And I wish I could give you a precise answer on that. I don't know. I occasionally ask people what they think. Guess people in the audience guess. What would you guess is the sort of the payback time by which, if you've done things the right way, you're actually ahead? And most people tend to give numbers somewhere between 3 months and 2 years. Personally, I think it's probably in the 12 to 18-month range, which is the time period after which you've forgotten what you did when you wrote that code a year or so ago. And so if it doesn't have a really clean structure, you're really suffering for it. But I don't know the answer to that, unfortunately. Unfortunately, I don't even know how we would measure it. People talk about that, but I don't know how to do the measurement to measure it. So the bottom line here, with the strategic approach, is you're investing. So you're taking a little bit of extra time today, but you get it back in the long run. Whereas with the tactical approach, you're basically borrowing time from the future. You'll go faster today, but you'll pay it back, and you'll pay it back with interest. And I often ask people, well, how much slower do you go in a really tactical code base? And I've heard answers as high as a factor of 10, that they've slowed down by a factor of 10. And actually, I've seen code bases I've worked in where I can believe that's the case if it's a really bad code base. So the difference can really be enormous, the payback, the loss of productivity from tactical programming. But then the question is, well, how much should I invest? Well, if you look at most Silicon Valley startups, the truth is they are totally tactical. No worries about design at all, just crank out as much code as they possibly can. They feel tremendous pressure to get their product out. They convince themselves, well, once we're successful and we have our IPO and we're all rich, we can hire an army of summer interns to come in and clean up all of our mess for us. And when you do this, the code base becomes completely spaghetti. And companies can succeed doing this, but the truth is it's really, really difficult to ever repair the damage. I bet there are very, very few companies that have ever been able to actually clean up a terrible code base. So my favorite poster child for this style of design is Facebook, now Meta. In the early days, Facebook had its mantra, which was move quickly and break things. And they did both of those. And developers, many of us thought this was cool. If you were a new developer at Facebook, it was assumed that you would have code running in production within 1 week of joining the company. You could tell your grandmother to go to this page and she could see code operating that you wrote. And that's very empowering for developers, but the code base became a complete wreck. Around this time, I'd been having discussions with my graduate students, some of who felt like they shouldn't have to put comments in their code, and why was I being so fussy about code? Nobody in the real world ever worried about that stuff. And by the way, Linux didn't have any comments in it. Why are you being so mean to us, making us put comments in our code, yada, yada, yada. And they went off to Facebook for a summer internship. And about halfway through the summer, they came back to visit. And they walked in, and their faces were ashen. They said, John, you can't believe it. Every Monday, they release all this new code, and nothing works. And you spend until the end of the day on Thursday to get back working. And then you only have one day to get new work done, and the next Monday, they break it all again. You can't believe it. They never complained about having to write comments again after that. And in fact, even Facebook, they eventually changed their mantra to move quickly with solid infrastructure, which I think really means move quickly, but damn it, stop breaking things. Now, Facebook has been successful. Mark Zuckerberg is crying all the way to the bank. And so clearly you can succeed writing really bad code. But does that mean you have to write bad code to succeed? And I would argue no. The good news is you can also succeed having a really strong design culture. And my two favorite examples are Google and VMware. So these were both companies that were kind of growing into their heyday between 2000 and 2010. And those companies were known as the place with really great engineers and very strong design cultures. And as a result, they basically got all of the good engineers in Silicon Valley, pretty much. I would talk to people from Google and VMware, and they would say, we never, ever have an offer turned down except by the other company of these two. Google only lost people to VMware, VMware only lost people to Google. And so I think that's important to realize, because here's a question for you. What is the best way to develop really high-quality software quickly? What's the best way to do it? The answer is hire the best engineers. We know there's this 10x difference between good engineers and bad engineers, so getting the best engineers is the most important thing. So do good engineers want to go to work for a company the code base is spaghetti code and you spend all your time fixing weird bugs? No, they'd rather go work for a company with a strong design culture. So I would argue it's enlightened self-interest to have a strong design culture in your company. It'll get you the better engineers. And actually, one thing I've noticed talking with the folks from TNG is it seems like an organization with a really strong design culture, which is fun to see. But then back to the question, but how much should you invest? How crazy do I go in the strategic approach? And my advice is I would say, make lots of smallish investments. What I would say is ask yourself, can I afford to spend, say, 10% more time on my current releases so the next feature will take 10% longer to get out? Or maybe 20%? Can I do that if that's going to allow my code base to be cleaner and allow me to keep developing quickly for years into the future? I think most companies would say, yeah. I think lots of companies say yes to 10%. Some might even say yes to 20%. So think of it in that range, where you spend some time doing careful design, write good documentation, and so on, and invest. And one of the most important things, the ways to invest, is to think about when you go in to make changes to code, to fix a bug or add a new feature. I think many people are often told, make the fewest possible changes so you don't break anything. So people are afraid. Now, of course, one of the reasons you do that is if your code base is a mess. If you have a clean code base, you may not have to do that. But I would say don't do that approach, because that's a tactical approach. That's going to cause complexity and kludges to build up. Instead, I would say ask yourself the following question. What your goal is when I'm finished with my change, ideally the system will look the way it would have if I had designed it from the start knowing everything I know today. That's the ideal. Now, that's not always achievable. I realize that could require enormous changes in some cases where you discover the architecture is fundamentally wrong. But think of that as your goal, and try and get as close to that goal as you reasonably can within the constraints of your organization and your current time restrictions and so on. But don't just settle for the fewest lines of code. And in general, I would say, always find something to improve. Every time you go to the code base, see if you can clean something up. Because the truth is, even if you're doing the best you possibly can, you're probably making something worse. Just honest truth. So to compensate for that, find something else to clean up. Of course, if you know what you're making dirty, don't do it in the first place, but typically you just don't realize you're doing something. So always find something to improve. And in general, ask yourself the question, is this the most I can afford to invest right now? And don't just ask that to yourself, ask it to your manager. And in the next all hands, ask it to your vice president of engineering. Is this the most, are we investing the most we can possibly afford to invest in software design? And then just look them in the eye and wait for them to answer. They'll probably squirm a little bit. And I think if you ask that question, I think you'll usually find that there are ways you can make things better. You can spend a little bit more time. So just do what you can within the constraints of your own organization. And the other thing I would say also is vote with your feet. If you're in a company that doesn't value software design, that encourages you to be tactical, that is making the code base messy and you don't happen to enjoy working for that, find a different company to work for. That's the best way to punish people, I think, who are doing bad design, is go work for companies where you can do design the right way. So back to the class. Is the course working? Well, I don't know for sure. What I've been meaning to do but haven't done yet is to go back and ask students after 5 or 10 years to see, did this class influence the way your career has evolved? Have you been able to use these techniques in industry and so on? And by the way, we can't make great programmers in 10 weeks. That's not possible. It's more like, I think, 5 to 10 years is how long it takes really for somebody to become a great programmer. So it's just the first step. But the energy in the class is really fun. And the evolution in the students over the course of the quarter is really interesting to see. In the first design reviews, where the students are reviewing each other's code in class, the students tend to be really tentative, because they're not sure what to criticize, and these are their friends. They don't want to insult their friends, so they're really very kind of tentative and avoid any serious criticism. And then I meet with the teams individually for an hour, and they see what real criticism is like. And by the way, they tend to really like those meetings. But after they've seen this, then by the end of the class, basically the code reviews are sort of no holds barred. People criticize each other, and discussions about whether one particular approach reduces complexity more than another different approach. And you can just see that the students are really thinking about how to code in ways they hadn't thought about before. So that's really fun to see. So it's clear that having an opportunity to really think about software design has an impact on people, changes the way they think. It's also been really interesting for me because all of the students are doing the same project. So I see 9 instances of the same problem solved, each in a different way. And so it's the reason I actually enjoy doing these code reviews, even though it sort of dominates my life for a week, 3 times out of the quarter, is that I can noodle over those, and I think we all know complexity when we see it, but then trying to figure out what caused it and how do we fix it. It's been a really interesting challenge for me so that I can give people meaningful feedback. And how do you think about code so that you can design it simply in the first place? And the result of that is it has changed my views on software design just from seeing all of these different pieces of code written. So the main one I mentioned is this importance of avoiding specialization, which I hadn't really thought about it very well. And then once I got an opportunity to see how it affects the same project done different ways, it was really informative for me. So after I'd been teaching the course a couple of years, I started giving talks about it, and then people would say, well, John, you ought to write a book about this. So eventually I had a sabbatical coming up, and I did that. I wrote this book called A Philosophy of Software Design. And the idea was just to capture the ideas from the class, hoping to reach more people, also hoping to stimulate discussion. I was hoping by putting this book out there, people would come back and would disagree with me and say, no, that's a stupid idea. Here's how you should be doing it instead. And that I would also learn from that. And then finally, I wanted to create terminology that we can use to talk about things. Like you can talk about deep versus shallow classes. Or now you can go in the middle of the night, come back and sneak in a little sign outside somebody's office door that says tactical tornado on it, and provide a little peer pressure on them to improve. So it's a relatively short book. I didn't want to write a 1,000-page book with 200 different pieces of advice that nobody would remember. So it's a relatively short book that focuses more on these kind of philosophical ideas. It's been around since 2018. There's now actually a German edition for the last couple of years. And I think I would argue the best way to use the book is along with code reviews, to use the book to talk about code and see how code does or does not conform to the ideas in the book and what are the consequences of that in the code. I think those philosophical ideas, are a little bit hard to internalize if you can't do it in the context of actually seeing code. So just to wrap up, is it possible to teach software design? Absolutely. I'm totally convinced it is possible to teach. The only problem with my approach is that it's not a scalable approach. I can only teach 18 people a year, so it's going to be hard to change the software industry at that rate. I've debated whether I should maybe bring in an army of TAs, because the class is oversubscribed. I can't admit everybody wants to take it. Should I have TAs doing it, but I worry that they would not be able to give the kind of quality feedback that I want students to have. So I've kept it with myself, reading all the code. I think that principles are emerging out of all of this. One of the things I wondered when I started the class and when I published the book also is there one right and true way to do software design? Only one way? Or is it possible that there could be two people who have very different approaches to software design, and yet they both produce really great code? Is it possible that there's fundamentally different styles that can also be good? And so I thought by publishing the book also, if there was a second style, I'd hear about it. But I haven't, actually. I haven't had somebody come and say, no, there's a totally different world out there. So I'm becoming, cautiously optimistic that in fact there really is a fundamental set of approaches that are right for software design. I don't claim to have all of them. I'm sure at least something in the book is wrong. I'm sure I'll find out over time. But I think it is possible to come up with a really clear set of principles for software design. And so my continuing goal is just to keep, and the reason I love giving talks like this, is to raise the sense of software design in the software community. So, I hope the book will attract discussion. There's a mailing list associated with the book on googlegroups.com. Relatively low traffic. It gets maybe, a message or two a month. It's not a super high traffic thing. And if you have any ideas about this, for example, if you think things in the book are just wrong, I'd love to hear about that. In some sense, honestly, negative feedback is generally more useful than positive feedback. It's nice, it's nice to get compliments, but negative feedback is what I can learn from. So if you have other ideas or you think there are things wrong in the book, let me know about it. And then I hope, eventually, maybe 5 or 10 years from now, maybe we'll be at a point where, in fact, our community does have a generally agreed upon set of software design principles that people can use to guide themselves as programmers. So let me stop there. Thank you for your attention, and I'd be happy to take questions.
Thank you very much for the talk. It was very good, and I have a question about the slides at the beginning about split methods and classes should be short, and that as a contradiction for what was the contradiction? Deep interfaces. My personal feeling is that maybe that's not a contradiction, and I could have a deep interface with internal small classes and methods. What are your thoughts about this?
Yes, so I would say things don't have to be long to be deep. Absolutely, you can have the best of both worlds. But you should only make things short if in doing so they can also be deep. So for example, if you have a long method, it might make sense to break that up into two smaller methods. That could absolutely be an improvement, but only if those methods are relatively independent of each other and have reasonably clean interfaces. If I break something up into two methods and I can't understand the first one without also looking at the code of the second one, I've gained nothing by separating them. In fact, I've made things worse because now I have these two things that are entangled, but they're distinct where I can't even see them at the same time. But I absolutely agree, in the best of all worlds, you have things that are, if not short, at least not very long, right, and very deep.
Okay. Hey. Thanks for the great talk. During the last 10 minutes of the talk, I was pondering about the implications for the software engineering community as a whole, about what you said, like you mentioned or emphasized, thinking about the structure, decoupling, decomposition, like all the things that make software hopefully great. The question is, what is the feedback mechanism we as a software engineering community could provide to foster, to implement everything you talked about, like bring everything back to the new generation, or ensure that we actually care about in our daily life?
That's an interesting question. I'm not sure I have the perfect answer for that, but I would say I think it starts with code reviews. I think it's really important for people to talk about software design and talk about it in a fairly concrete way. So now, how many people here in organizations where you do code reviews? I would guess many of you, most. That's great. That's good. Now, how many of you in your code reviews you actually try and talk about deeper design issues as opposed to coding style and bugs, stuff like that? How many of you try and address real design issues in your code reviews? That's great. That's actually more hands than I would have expected. Still only a small fraction of the people doing code reviews. So I would say the first step is to try and do design things, talk about design in the code reviews. Even if, now in the ideal world, you'll be able to talk about design in the code reviews, then people will be able to go back and repair the design problems. Even if you don't think there'll be time for that, I think it's still worthwhile to talk about those design problems because that will heighten people's awareness and so they're less likely to make mistakes in the future. So to me, that's I think where it starts in terms of looking at people's code and sharing ideas about design.
Hi. Thanks very much for the talk. I could come to the stage and hug you for some things that you said. Of course, we are all great. We are all here in the room, we are all capable of doing great design, but somehow bad design happens every day. So there's something, I think, a social issue connected to this too. And I very much like about the course idea that one gets compared, or let me start from this way, there are some professions and some things, skills, where there is wide overconfidence in one's own competency. Like, I mean, we in Germany, we are car drivers, as you might have noticed here. So 85% of Germans say they rate their own capability in car driving above average, which is... and somehow my idea about design competency in software engineering, and I might now get a bit of a... I think there is something in this too. So now if you say, let's invest more into design, can lead, just as a possibility to people investing more without having the capability, but getting a reflection on this. Where am I actually standing in my capability of software design and where should I go? I like this aspect very much because you get a feedback through your course design on where you stand and where you should improve. What do you think about this aspect, which is kind of a social aspect of the thing?
Well, my first thought is if you want to be a good software designer, you have to think of yourself as actually not being a great software designer in the sense that the person who is totally confident in their design skills is probably the one that's going to have the worst design. I mean, I make design mistakes all the time. I think that one of the things to realize is you will make mistakes. You will not get it right. You know, when I'm designing a new class, I typically have to do it 3 times to get it right. The first one, I get halfway through implementing it, and it makes me sick, and I have to throw it away. And the second one, I can get all the way through implementing it, it looks okay, but there's zillions of little things wrong with it, and then the third iteration is usually something I'm happy about. So I think you have to have this mentality that, yes, we're going to make mistakes, and that's totally fine. In fact, the way you learn is by making mistakes. You know, if you think about how we do education, education is simply creating a safe environment in which people can make mistakes and learn from them. I mean, that's the whole idea behind the software design class. I tell students at the beginning, you are all going to make mistakes. I'm going to criticize, and I'm going to criticize mercilessly every little detail. It doesn't mean you're a bad person. It just means you're learning. So I think if you make this mentality that I don't think you need to worry about where do I rank in all software designers. All you need to really worry about is I need to get a lot better, and I can get a lot better. And so just, you know, every day you should wake up thinking, I made 3 mistakes yesterday. I need to figure out what at least 1 or 2 of those are and fix them today. And if you take that mentality, you will become a great software designer. I'm sure of it. It's when you get to the point where you think you know it all, you know how to do it, that's when you're in trouble.
We have a question from our remote viewers as well, which is, I think, a very funny one. What's a good strategy for dealing with a tactical tornado?
What's a good strategy? Do I have to be humane? Well, I mean, I've always believed in blunt feedback, straight feedback. I like being in environments where, you know, people can criticize each other without necessarily believing it's criticizing the person. And so I would take them aside and say, look, at solving 80% of the problem doesn't help us. And when you introduce little things, they just accumulate. Someday somebody will have to fix those things. And so you should try and find a way to create less technical debt for us. I just take the person aside and talk to them.
Okay, I think we could continue for many more hours here. I know there's still more questions, so please come to the front. We have a coffee break right now until about 4:15. So if you have more questions for John, please come to the front. But for now, let's give one more round of applause to our speaker. Thank you.